What is big data? The term is used loosely, even ambiguously at times, but there are some ideas that usages of the term have in common. First off, big data is complex. Collecting and storing it can be complicated, algorithms applied to it can be very complex, and the results can be sophisticated and even prone to misinterpretation. Let's start out with data. We tend to think of data in rectangular arrays, and data sets are in terms of rows of observations and columns of features, something like a spreadsheet. And we may have several spreadsheets, so a rectangular box of rectangles. A collection of spreadsheets, for example. Consequently, data sets tend to be large. If you've got 100 spreadsheets with 100 observations of 100 factors, that's 1,000,000 data points. For example, look at movie rental data. Your features are the movies. Your observations are each of the individual viewers' ratings of the movies. And you have those viewers rating movies each and every day. Millions of viewers times thousands of movies times thousands of days. Now you've got trillions of data points. Another example is wiki logs. So all those Wikipedia pages, the number of requests per hour per page has been recorded every hour since 2007. That means that you have pages and 24-hour periods, and the data here is page requests or hits during a given hour on a given day. So that's about 5,000,000 pages, 24 hours, 2,750 days approximately. That's about 325 billion hit counts that make up the Wikilogs data. And this is just the tip of the iceberg. Social networks, housing prices, handwriting recognition, genetic experiments, science experiments in general are producing huge amounts of data. But large data sets are not new. Ports have tracked tides for centuries. Hundreds of ports have recorded thousands of high and low tides over many centuries. But that's not what we would call big data. Also, we have census data. Countries have been conducting a census of their population on regular intervals for millennia, thousands and thousands of years. But again, not what we would consider big data. So what do we mean by big data? Well, big data refers to data sets that are not only large, they're also complex. Complexity refers to dimensionality, and dimensionality is related to independence. So for instance, if we had a data set which was all the squares whose sides range from a length of 1 to a length of 1,000,000, so we've got 1,000,000 squares and the characteristics of those squares, that's a very large data set, but it's not very complex. So complexity requires high dimensionality, and the dimensionality of a data set is related to the dependence or independence of its features. The geometric features of squares data is very large, but there is only one independent variable. For instance, we can take the area is equal to the side squared, the perimeter is 4 times the side, the diagonal is the square root of 2 times the side, the dimension, number of vertices, number of edges, those are all constant. So there's only one independent variable. Now, we could use perimeter instead of side because side is equal to the perimeter over 4. And so we can choose, but still, there's only one independent variable. Data with only one independent variable, not really difficult to work with in general. But if you have large numbers of independent variables, now that's a lot more challenging. Why? Because each independent factor or variable represents a process that independently contributes to the experiment. For example, if we toss a coin, then all we need is one variable to track the outcome of one single coin toss. Either a 1 for heads or a 0 for tails, and x is then either 1 or 0. So this is only one-dimensional, only one variable. Similarly, if you had a random number generator generating numbers between 0 and 1, even though it's now a continuum and we can obtain any number between 0 and 1, we only require one variable x. That's again one-dimensional. If you've got a number x and y chosen independently and uniformly from the unit interval, however, then you need an x and a y axis. And points that you could get by independently and uniformly choosing the x and the y have to be pairs or points in the Cartesian plane, and all possible such points where you choose x uniformly and randomly and y uniformly and randomly from the unit interval, and you choose them independently, well, that's all the numbers in the unit square. And that's two-dimensional. Now, if you have many independent variables, then you have high dimensionality. And you can think of this high dimensionality exactly as you would think of it already. You keep adding axes. To an x1, x2, you add an x3 axis, and then an x4 axis, an x5, and so on and so forth. And there you get high dimensionality, and that's where complexity can live. Now, let me just mention that there are actually several notions of independence in mathematics and statistics. Dimensionality is based on the notion of linear independence. For example, let's look at microarray data. Genes were activated by the experiment, and that was class 1. And class 0, genes not activated by the experiment. So we want to figure out which genes are in class 1 and which genes are not in class 1. In other words, they're in class 0. So which genes got activated by the experiment? Now, there's 22,000 genes or so, approximately. So the experiment in question certainly activated genes or failed to activate genes, but genes can be activated by many different independent processes: metabolism, respiration, DNA repair, and each one of these 7 subjects has their metabolism, respiration, all these different processes independent of the other 7. Now, independence itself is not enough. So let's look at data that is in the form of speedometer readings since 3 p.m. on a certain day for N automobiles on a certain stretch of highway. How the automobiles are related is what determines whether or not the data set is complex. In other words, it's the driving down a highway process that may or may not be complex. If the process is not complex, then the data collected from it also will not be complex. Conversely, if the process is complex, then the data may be complex. But now it depends on how much and how carefully it was sampled. That's what we call veracity. And like any data, you can have poorly collected big data sets, and therefore how you collect data and how much you collect is part of the process, and that's what's known as veracity. So let's look at a process that's not complex. Suppose we have automobiles sufficiently far apart such that they're moving independently, but there's a speed that is desired on the highway, so they have an overall average speed. That means we are looking at a model of the form data equals the average speed plus the noise. In mathematical notation, if S sub j is a speedometer readout of the jth car at time t, then our model is S sub j equals mu plus R sub j, where mu is the average speed over all the automobiles, and R sub j is the noise or the random variation in the driving of the jth car at time t. Now notice that mu is the average, so the average of the R sub j's has to be 0, because it shouldn't contribute anything to the fact that mu is the average. Now, if we've got automobiles sufficiently far apart, driving with an overall average speed, then we get independent observations. So we have the independence. However, this is not complex, nor would we even call it big data. Why? Because even though it's independent, they have this simple relationship of all trying to drive the same speed. And not surprisingly, they average to that common speed. So for instance, if you take the average of the first two, it's less variation around the average speed of 40. The first three average to be close to 40. The first four even closer to being an average of 40 at all times. And of course, if we average all of them, then it's practically a straight line, a horizontal line corresponding to a speed of 40. So dependence is also necessary. And we get complex data from processes that have many independent variables with dependencies, relationships, dependent variables that are not linear and very complicated. Notice that we've shown, in some sense, randomness does not produce complexity. But driving can be complex. So let's go back to our speedometer data. But this time, suppose the cars are close enough together that they have to interact with each other. They start out at constant speed, but their interactions are necessarily nonlinear, and therefore a traffic jam necessarily emerges even though they're trying to all drive at a constant speed. This may seem strange, but you can actually do it with actual cars. You have this nonlinear action and a traffic jam emerges. So,
for the first time, Japanese researchers conducted a real-life experiment that shows how some traffic jams appear for no apparent reason. They placed 22 vehicles on a single track and asked the drivers to cruise round at a constant speed of 30 kilometers an hour. At first, traffic moved smoothly, but soon the distance between cars started to vary and vehicles clumped together at one point on the track, where the jam spread backwards around the track like a shockwave at a rate of about 20 kilometers an hour. Real-life jams move backwards at about the same speed.
so the speedometer data from these 22 cars is necessarily complex. So when we have dependence, what do we really mean? Well, we could have regular dependence, regular variables, which are variables that depend smoothly and simply on other variables, like sinusoidal oscillations as functions of time or exponential growth as functions of time. Random variables that obtain values randomly and in some sense independently, at least in part. There are also chaotic variables that depend on other variables in an unpredictable but not random fashion. Now that may seem strange, unpredictable but not random, but you have to realize that unpredictable refers to human limitations. The digits of pi are not random, but we humans cannot predict them. The motion of an individual atom in a protein is completely deterministic and is not random. But here is an actual protein that causes a certain type of cystic fibrosis, and this is a molecular dynamics simulation that took a few days on the ETSU Cluster Night Rider. And you see different representations, and everything that you see here is completely deterministic. There's a pattern here, amazingly enough. So, even though there's a pattern, however, the pattern is beyond our comprehension. It's just too complicated for humans to comprehend. So now we have a working definition of complexity. A complex system is high-dimensional, many independent variables with regular and chaotic variables that are related in unfamiliar ways. The underlying structure is complicated. And complex data is what comes from complex systems.